In the two previous videos, we looked at how to describe lines in three-dimensional space and how to describe planes in three-dimensional space. In this video, we're going to look at a couple examples where we combine lines and planes together. So for the first example, we want to find a point of intersection between a line and a plane. So we want to find the point of intersection between the line described by r of t. So it's going to be 2 minus 3t, 1 plus 4t, and negative 3 minus t. Right? And the plane that we're going to describe by the linear equation 4x minus y plus 2z equals 5. Okay. So we have a line and we have a plane, and we want to know when do they intersect. I guess the first question to really look at, or thing to consider, is that it is possible for a line and a plane not to intersect. For example, you could have the x-axis as the line, and you could have the plane z equals 2. Lying 2 units above that axis. So those will never intersect. In this case, we will see that they do intersect. But in the case that we have a line and a plane that do not intersect, this approach will show that is not the case. Okay? And so the way that we want to look at this particular problem is that if we look at points on the line have to have these three coordinates for x, y, and z for some value of t. And so we can actually just take those parametric equations and substitute them into the equation of the plane for the appropriate variables. So if I have a point x, y, z that is on both the line and the plane, it must satisfy the following. It must satisfy 4 times 2 minus 3t minus 1 plus 4t plus 2 times negative 3 minus t equals to 5. Right? So any point must satisfy this equation. And so when we go through here, we're going to distribute. So we have 8 minus 12t minus 1 minus 4t minus 6 minus 2t equals 5. So we have negative 12t minus 4t minus 2t is negative 18t. And then I have 8 minus 1 minus 6, so that would be 1. And so negative 18t is equal to 4, and therefore t is equal to negative 4 over 18, or negative 2/9. Right? So the intersection point has to satisfy the value of the parameter of negative 2/9. Right? So we're just going to compute r of 2/9, and this will give us the point on the line corresponding to this particular value of t. So we're going to have 2 minus 3 times negative 2/9, 1 plus 4 times negative 2/9, and negative 3 minus negative 2/9. Right, so this will be our point. And when we go through and do the arithmetic, I believe we get the point 8/3, 1/9, and negative 25/9. And so our intersection point is the point 8/3, 1/9, negative 25/9. Okay. Right, and so this problem is basically just algebra. It's understanding what the vector form of the line and the linear form of the plane represent. But really the actual mathematics that we have to do here is just some basic algebra. So for the next example, let's take a look at what happens if we want to find the intersection of two planes. All right, we just looked at how to find the intersection of a line in a plane. The next step would be intersecting two planes. Now the one thing to think about here is if we have two planes and they intersect, that intersection is going to be a line. So we want to find the equation of the line of intersection. Of the following two planes. So the first plane is going to be x minus 2y plus 4z equals 7. And the second plane is going to be 2x minus y plus 3z equals 0. Right, so I have these two planes. Right, so we want to find the equation of a line, and we know to do that we need to find two things. We need to find a point, and we need to find a direction vector. Okay? And so the key thing here to observe is that this line of intersection has to lie in both planes. And therefore, it must be, since it's in the first plane, it must be orthogonal to the normal vector for that first plane. Right? So we know the normal vector for our first plane here. We can just read it from the equation. It's going to be 1, negative 2, and 4. It's going to be those coefficients of x, y, and z. And from the second plane, while we're here, I'm just going to go ahead and write this down. The normal vector for the second plane is 2, negative 1, 3. So this is one of the nice things about the linear equation of a plane, is that the normal vector can be read off just as the coefficients of x, y, and z. Right? And so the line that we want is on both planes. So if I have a vector on that line, then it has to be orthogonal to n1 because the vector lies in the first plane. And it also has to be orthogonal to n2 because the vector lies in the second plane. And so the key here that I'll actually write down, I just said this out loud a couple different ways, but the intersection line is orthogonal to both n1 and n2. Right? And so to find a direction vector for this line, what we need is to find a vector that's orthogonal to both n1 and n2. And so the obvious way to do that is to take their cross product. Right? So we have n1 is negative 1, negative 2, and 4, and 2, negative 1, and 3. Right, so when we do this, for I, we're going to get negative 6 plus 4, that's negative 2. For j, we get 3 minus 8 is negative 5j. And for k, we get negative 1 plus 4, which is positive 3. So we have the vector in component form, negative 2, negative 5, and 3. Right? So this is going to be my direction vector, which we've been calling v before. So this will be the direction of my line. And we got that by finding a vector that is orthogonal to the normal vectors to both planes, and anything that's orthogonal to the normal vector of a plane must be in that plane. Right? So the last thing we need to do is find a point on this line. And so we can do this in any number of ways. So for example, one thing we might do is we can just pick a certain coordinate to be a certain value. So I'm going to just take something simple. I'm going to say, well, I'm just going to set z equal to 0. Right? And if z is equal to 0, I go back to my two equations for the planes, and this tells me that for x and y, I need to choose x and y so that x minus 2y is equal to 7. That'll satisfy the first plane. and then 2x minus y equals 0 will satisfy the second plane. So I've just replaced the z in the plane equations with 0. And at this point, we have a system of equations with two variables, which we can solve. And so there's a variety of ways we can solve this. For example, we might keep the first equation as is and multiply the second equation by -2. And if we did that, we would get -4x plus 2y equals 0. All right, when we add these together, I get x minus 4x, which is -3x. The y terms cancel out, and 7 plus 0 is 7. So we get an x-coordinate of -7/3. So I started by picking z to be 0. We just found that x has to be -7/3. And then we can use either of the equations to find y. So from the second equation, 2x minus y equals 0. Since x is -7/3, 2 times -7/3 must equal y. I'm going to add the y over there. And so this is -14/3. And that's our value for y. And so we have a point on the line, which we just found. So it's -7/3, -14/3, and 0. And we have a direction, which was the vector we found previously, which was -2, -5, and 3. Right? And so our equation of our vector form of our line, r of t, it's going to be -7/3 minus 2t, -14/3 minus 5t, and 0 plus 3t. So this is the equation. This is the vector form of the line, and we want to take t to go from -infinity to infinity. So we want to look at one more example involving lines and planes. And in this case, what we want to do is we want to find the shortest distance between a point. All right, in point P, we're going to be given 3, 1, -2. And the plane given by 2x minus 3y plus 6z equals 2. Before we go about solving this particular problem, it's probably best if we look at this problem more generally, where we have some plane and some point, and we want to find the shortest distance from that point to the plane. We can kind of come up with a strategy for how to solve this, and then apply that strategy to this particular instance. Right, so let's say we have a plane in 3 space. I'm just going to draw it as a rectangle, oriented sort of nicely, but it could be any plane in 3 space. And I have some point, which I'm going to call P, that lives somewhere outside of the plane. Of course, if P were on the plane, then the answer to this problem would be 0, and we're done. So let's assume the point is not on the plane, because in the example we're going to look at, that point is not on the plane. Right? Now, what we're trying to do is we want to find the shortest distance from the point to the plane. So geometrically, the way that we can think of that is if I would drop a segment down from P to the plane, and maybe it intersects the plane right there at a right angle, the goal of this kind of a problem is to find the length of that dotted segment. All right, that would be the shortest distance between the point and the plane, is to connect that point P with the plane with a segment that is orthogonal to the plane. Now, I don't know that point of intersection that I just drew, because I don't know the line that I need to get that point of intersection. And it turns out I don't need to. So let's say that I just knew some other point. I'm going to call it A that lives on the plane. Right? We could compute vector AP. So this is vector AP. Right? So we can connect. We could easily compute that vector as long as we can find a point A on the plane, which is not too terribly difficult to do. And then what we want to observe is that this dotted line here, because this dotted segment is perpendicular, its direction is the normal vector of my plane. Right? And so this dotted line is actually the projection, the orthogonal projection of line AP, or a vector AP, onto the normal vector n. Right? And you can kind of see this on this particular picture. If we had a light on the left side of the screen and we shined it directly right, that dotted segment would be the shadow of vector AP on the normal vector, which would be some version of that direction. We don't know if it's further than P or less than P, but along that line that contains the normal vector, the dotted black line would be the shadow of the red vector. And so the shortest distance between the point and a plane is going to be the projection of some vector from some point in the plane to my point P onto the normal vector. And so that'll actually give us the vector from the plane. And so to find the shortest distance, we need the magnitude of that vector. So with that in mind, the distance that we're looking for, which I'm going to call D, is going to be the magnitude of the projection of some vector AP onto the normal vector of n. Okay. So we need to remember, what is the projection? So the projection of AP onto n is going to be the dot product of AP and n divided by the magnitude of n squared times vector n. Okay. And so when we compute this, what we see is that we're going to get in the top, we're going to take, it looks like the norm, but this is actually, in this case, the absolute value of AP dot n. Of course, that is a real number, but it could be negative, and we don't want that. We want a distance, so we want the positive version of that. And then we have the norm squared in the denominator. That's just a number, but then we're also taking the norm of n here, so we end up with just the norm of n, or the magnitude of n. There. And so this is the distance that we want to compute. We have to pick a number A, or pick a point A in the plane. We are given point P, and the vector n we're not directly given, but we can read it really quickly from the equation of the plane. And so what we have to do is we have to choose some point A on the plane. And usually it doesn't matter what we pick. We just want to pick something that's easy to see. And so I noticed that if I let y and z be 0 in the equation of my plane, I get 2x equals 2, which clearly has the solution of 1. So it's pretty easy to pick a point like 1, 0, 0 that would be on our plane. We have 2 minus 0 plus 0 equals 2. Right? So there is my point A. And so once I do that, the rest of this is just vector algebra. So I need to compute the vector AP. Right? So we have 3 minus 1 is 2, 1 minus 0 is 1, negative 2 minus 0 is negative 2. So AP is the vector 2, 1, negative 2. I also need to know the vector n, the normal vector for my plane. But remember that we can just read off from the coefficients of the plane, of the equation. So that's 2, negative 3, and 6. I then need the dot product of these. So AP dot n will be 2 times 2 plus 1 times negative 3 plus negative 2 times 6. So it looks like we get 4 minus 3 minus 12, which is negative 11. And the other thing we need to know is the magnitude of n, which is the square root of 4 plus 9 plus 36, which is square root of 49, which is 7. Right, so now we have literally everything we need. So our distance d is going to be the absolute value of this dot product, AP dot n, over the magnitude of n. So we get the absolute value of negative 11, which is 11, over the magnitude of n, which is 7. So this point, the shortest distance from that point, 3, 1, negative 2, to the plane 2x minus 3y plus 6z equals 2, is 11 over 7. Okay? And so this really is just a kind of a natural application of the orthogonal projection onto the normal vector. Right? And these are the kinds of problems where those orthogonal projections are quite handy.